In our previous lecture, we have seen the Maxwell's equation which are applicable for magnetostatics, and those equations were divergence of B is equal to 0 and curl of B is equal to mu naught J. Now since the curl is not 0 here, then it implies that we cannot find a scalar whose gradient is equal to B. In electrostatics, we have seen that electrostatic electric field was curl free and we could find a potential phi whose gradient was equal to the electrostatic electric field. However, since here it is non-zero, then we cannot find a scalar quantity whose gradient will give us magnetic flux density. However, we know that divergence of a curl is always zero. So it implies that we can make B to be curl of a quantity. However, now this quantity A, although called as vector potential or magnetic vector potential, it has a lot of freedom. Now you can see that this A is not a unique quantity. Like if there is some A dash which is some A plus some constant vector K, then its gradient del cross A dash is equal to del cross A plus K is equal to del cross A plus del cross K, and since this is a constant vector it will be equal to 0. So you see that for A dash also we have the same curl. So this implies that A is not unique here. We can add some constant vector to it. Furthermore, this is similar to the condition in electrostatics wherein we saw that the potential was not unique. We could have a constant potential always added to it. So we need some boundary conditions as well as some other conditions so that we can find the field from vector potential. Now there is further more freedom inherent in the vector potential. Let us see how. Let us say B is equal to del cross A dash is equal to del cross A, or I can write del cross A dash minus A is equal to 0. What does it mean? It means that this A dash minus A can be written as gradient of some scalar quantity, because gradient always has its curl equal to 0. So this A dash minus A can be written as gradient of a scalar quantity. So I can write that A dash is equal to A plus gradient of this quantity. So you see that this A prime is still having more freedom. In addition to that, we can add some constant vector. Here we can make this psi any value, so that we always get this del cross A prime is equal to del cross A. Or you can see that del dot A prime is equal to del dot A plus del dot del psi, or we can write del dot A prime is equal to del dot A plus del square psi. Now I can take this psi such that I always have the required equation that del cross A prime is equal to B is equal to del cross A. So still we have so much choice left with us. Now, to make our life simpler, at least in magnetostatics, we have freedom to choose the divergence of A, and we will see what choice will be better for us. So you see that del dot A prime was equal to del dot A plus del square psi. Now, the best possible scenario, at least in magnetostatics, is possible when I choose this equal to 0. Then I can choose this psi anything such that we have at least some satisfaction or surety about A and A prime. However, even if we fix that this del dot A is equal to 0, even then we will not be able to get a unique A, because still we require at least a boundary condition, like in scalar potential we had the condition that potential at infinity was equal to 0. So similar to it, we need to put a condition that either we have some boundary condition or we should have A such that it should be tending to 0 at infinity. Only then we will have some uniqueness to it. So you see that this vector potential is not a unique quantity. However, we don't need it to be unique for the calculation of the flux density. As you can see that we will always have del cross A is equal to the magnetic flux density, and even though this A is not unique, but if we have some boundary condition and we put this del dot A is equal to 0, then we will have some uniqueness to it. Now this condition del dot A is called as fixing the gauge, and for magnetostatics this quantity del dot A is equal to 0 is called Coulomb's gauge. Now we need to get more familiar with this vector potential, because it is little more difficult compared to scalar potential. So let us get more acquainted to it. So let us take a very simple case. Let us say that we have a uniform field which is constant and is in the direction of z axis. So let us say there is a vector potential A whose curl will give us this field. So you see that Bx, that is the x component of this field, is equal to 0 is equal to dou by dou y of Az minus dou by dou z of Ay, and By is again equal to 0, that is the y component is equal to 0, dou by dou z of Ax minus dou by dou x of Az, and Bz, the z component is equal to B naught is equal to dou by dou x of Ay minus dou by dou y of Ax. This is nothing but I have solved or this further shown the curl of A in its component form. Express the curl in this form. Now we have a lot of choice. Like if I let us say what are the choice, what can be the choice we can have for choosing the Ax, Ay, Az, so that we can have this field. So first choice can be that Ay is equal to x times B naught, Ax is equal to 0, and Az is equal to 0. So if I put this value in this, so you will find that only this will be equal to 0, this will be equal to 0, only this will survive and it will be equal to B naught. The second choice will be Ax is equal to minus yb naught, Ay is equal to 0, and Az is equal to 0. If I put this value, we will find that this again is equal to 0, this again is equal to 0, and this will be 0. However, this will not be 0, it will be equal to minus of minus b naught, or is equal to b naught. So you see, these two different vector potentials will give us the same field. Now we can have further option, that I can have this third option for vector potential, which is combination of both. That is, the vector potential is such that the ay is equal to 1 by 2 x b naught, ax is equal to minus 1 by 2 y b naught, and az is equal to 0. So again, we can verify that this will be equal to 0, this will be also equal to 0, and this will give us b naught by 2 plus b naught by 2 is equal to b naught. Again, this is also fulfilling our requirement. But this choice of A is having a peculiar quality. Let us see what it is. Let us say this is x-axis, this is y-axis, and z-axis is out of the plane of the paper. Now the vector potential is having x component, the x component proportional to the y, and y component is proportional to the x. That is, if I am here, so y component will be 1 by twice of x b naught, and ax will be minus 1 by 2 y of b naught. So at this point x is equal to 0. So you see that the y component of A, the vector potential, will be 0, and x component will be like this. That is, there will not be any y component, only x component will be there. Again, if I am here, then you see that y is equal to 0. Then the vector potential will only have y component, its x component will be 0, that is, this component will be 0. So you see that if I take any point in between, let me draw it further, let us say like this. So if I take a point here, then x component as well as the y component will be like this. That is, x component will be negative proportional to y, and y component will be positive proportional to x. So this is ay and this is ax. So you see that this vector potential is going to follow this curve. That is, it will be circular. And you see that any vector r can be written as, let us see, if it is x and this is y, then vector r can be written as x ax plus y ay. So if you take r dot a, where we have a is equal to 1 by 2 y minus ax b naught plus 1 by 2 x b naught ay plus 0. I have put this is ax, this is ay. So if I take this dot product, you will find that x ax plus y ay dot product of b naught by 2 minus y by 2 ax plus x by 2 ay, or this will give us minus xy by 2 b naught plus xy by 2 b naught equal to 0. So you see that this vector potential is always perpendicular to this radial vector. So again this proves us that vector potential will always be tangential to this curve. It will follow this circle and it always will be tangential to this curve. So if I need to write it in a vector form, I can write it as that A can be written as, because it is perpendicular to R, as well as it is perpendicular to B naught and its magnitude is half of this. So I can write it as A is equal to half of, I have written it in other form, B naught cross R. Otherwise, I will get a negative value. So if you see that B is equal to B naught AZ and R is equal to R A phi, sorry AR, then B naught AZ cross R AR 1 by 2 of course will be 1 by 2 B naught R, and what will be Z cross R? It will be 1 by 2 B naught R A phi, because if we are talking in cylindrical coordinate form, then AZ cross AR is going to give us A phi, and of course this is always in A phi direction. This is always A phi direction. So you see that A can be written as half of 1 by 2 B naught cross R. So in this way you can see that this uniform magnetic field in z direction, so this is, let us say, z direction, this will be possible only if the vector potential is like this, that is always in tangential direction like this. And its value is A is equal to 1 by 2 B naught or B cross R, where R was the vector from the center to the point, and this was B. So B cross R is always going to give us the vector potential. So in this way we can have a feel of vector potential, that its curl will always give us the magnetic flux density. Now curl is always going to give us the circulation part or the uh, vortex part of the field. So if you see that if I define a field which is circular in nature like this, so it is a vortex and its curl will always point perpendicular to like this. So this again gives us the physical picture. So if A is like this, then its curl will be like this. So this also again gives the physical picture, and it should clear uh, how we can visualize vector potential from a given field, or we can visualize a field from a given vector potential. Now this kind of field which we have just discussed, that is uniform in a direction, can be found in a solenoid. Inside a solenoid you will see that if current is like this, then field will always be like this. Then you see that this vector potential is also like this and current is also like this. So this gives us a hint that vector potential is usually in the direction of current. Now we will further see the vector Poisson's equation, and this will further, establish this idea. So let us try to, find the vectors Poisson equation in the next slide. According to the Maxwell's equation for magnetostatics, the curl of B is equal to mu naught J, or if I write in the vector potential form, del cross A is equal to mu naught J. Now I can expand it using back cab rule. So this curl of A can be written as gradient of divergence of A minus divergence of gradient of A, or del dot A minus del square A. This identity we have seen a lot of times earlier also, so it should be now in the mind of everybody if you are following my lectures. So you see that we have already chosen that this del dot A is equal to 0, and you now have better idea why did we choose it, because it is going to make our lives easy, at least for magnetostatics part when we are dealing with steady currents. So you will find that now I can write it as minus del square A is equal to mu naught J. Now you should note that we are dealing with the materials for which mu is, or at least we are now working with vacuum, so we need to not worry. However, for magnetic materials, this mu can vary with position, then we will have to worry about its variation with the gradient and the curl, that we will see when we will study the magnetic materials. For now, we will just take the simple case. So I can write del square A is equal to minus mu naught J. Now in Cartesian coordinate form, del square A can be simply written as dou square by dou x square ax plus dou square by dou y square ay plus dou square by dou z square az, where a is simply in component form written as ax ay plus az. Now I can write it is equal to minus mu naught J. Now I will express J in its component form, jx ax plus jy ay plus jz az. Now of course this is components also, so I need to write the vector also, unit vector with them. So on comparing the components, I can write now three scalar equations, and this equation is called vector Poisson equation, because it is similar to the scalar Poisson equation which we have seen in our one of previous lectures. So here we are going to have three scalar equations, and those will be equal to dou square ax by dou x square is equal to minus mu naught jx. At least in Cartesian form it is very simple. Dou square ay by dou y square is equal to minus mu naught jy, and dou square az by dou z square is equal to minus mu naught jz. So in Cartesian coordinate form, the equations are very simple. In other coordinate system, the curvilinear system, this del square operator will not be so much simple. We have seen in our previous lectures how to find this del square, the Laplacian operator, in various coordinate system. In that we will have various term 1 by dou r or something like this. So it will be difficult and it will not be that much easy to solve. But at least for Cartesian coordinate system, we can write these three separate scalar equations which are similar to Poisson's equation. If I write mu naught j is equivalent to minus rho by epsilon naught. So you have seen that del square phi is equal to minus rho by epsilon naught had a solution phi is equal to 1 upon 4 pi epsilon naught rho dv dash over the vector from source to the field point, and integration was on the source volume. So this equation had this solution. So the equation del square ax is equal to minus mu naught jx will be having similar solution because similar equations have similar solution. So I can write ax is equal to, now you see rho by epsilon naught is changed to mu naught j, that is I have to multiply or replace rho by epsilon naught with mu naught j. So I can write ax in this equation. I can write by replacing rho by epsilon naught with mu naught j as mu naught upon 4 pi over the volume v dash jx dv dash over r, where this r is the magnitude of the vector from source to field point. So in this way we can find all the three components of this scalar vector potential. So ay will be mu naught upon 4 pi jy dv dash over r over full volume v dash, and az is equal to mu naught upon 4 pi jz r dv dash over full volume v dash, and for the sake of completeness on this slide I will write ax also again. So if I write a is equal to ax plus ay plus az, I can now from these equations I can add them with component, then I can have a is equal to mu naught upon 4 pi jx ax dv dash over r plus mu naught upon 4 pi jy ay dv dash over r plus mu naught upon 4 pi jz az dv dash upon r, and all this integral is on the same volume where the source current is there. So a can be written as, I can take now mu naught upon 4 pi common, and I can take this integral like this now, v dash 1 by r is outside jx ax plus jy ay plus jz az over the volume full v dash. So this is now again the vector current density. So mu naught upon 4 pi j vector over r dv dash over the whole volume v dash. So in this way we can find the vector magnetic potential from the source current density, and this is the volume current density. And you will find that it is easier to calculate this vector potential first. From that we can find B is equal to del cross A. Now there is one good result by using Stokes theorem. Let us see what it is. So flux of magnetic field through any surface area S can be written as B dot ds over the full surface area S. Now I can write B is equal to del cross A dot ds over full surface area S. Now I will use Stokes theorem on this. I can write A dot dl over the full curve C enclosing this surface S should give me the total flux of the magnetic field through that surface area. So if this is a surface area and some magnetic field is there, then the flux of this magnetic field from this surface area can be simply calculated if I know this line integral. If I know the circulation of A on this enclosing curve C of the surface area S, I can clearly find the flux of magnetic field through that surface area. This result we will use in determining either A or B from whenever required. And you will find that it is sometimes easier to visualize A than B, because when we will study induction or a transformer core, you will find that B is only in the core, maximum part is in the core, only very small leakage flux is there. So the coil is wound here like this, or it may be wound like this. So you will see that how can we explain that this conductor knows how much flux is inside it, because this conductor is not where the flux is. This conductor is so far away from the flux lines, but still it knows that the voltage induced in it will be d phi by dt. So we can easily explain using the vector potential. Although flux magnetic field will be zero, but you will find that the vector potential will not be zero here. It will be like this, circulating like this. Of course its value will be reducing with the distance. That's why I am showing little bigger arrow when closer to the core. So we can easily explain physically using the vector potential instead of the magnetic field this phenomena. That is how the wire will come to know how much voltage it has to induce. Now you will find that we can find this A if we know B. Although usually we will find B from A, but in some simple cases where ampere circuit law is easier to apply, we can find or calculate the other way around. We can find first B then A. That we will do in the next lecture, while we will calculate A for some given configurations. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel and join our Telegram group, whose link is given in the description of this video. Thank you.